Core to the cloud, and let's talk a little bit about how you can also own a house when you're 24, let's say. And for the sake of it, why not buy your parents a house as well? Anyway, so before we get started today, I have been getting a lot of questions about getting a job in tech, okay? Hopefully you guys are very familiar with the process, but I know that maybe not everybody talks about what exactly the process looks like. So here are just like some tips that like this is my take on what I would do if I was an undergraduate again, and how I would try to like maximize my probability. So basically, every single summer that you can, you should do something. So the first thing is, if you did not do something, like anything that you have already not done, it's in the past, forget about it, it does not matter, you know? Like there is no point in being like, damn, I don't know how to code, so I can't get a job, you know? Or damn, I didn't get my internship last summer, so I should just give up. Literally 0 point in ever thinking that way. Just, if it didn't happen, forget about it and focus on the future going forward, right? So going forward, what you want to do is you want to do something related to tech every summer. The worst thing you can do is have a summer that is, I did nothing, okay? So, but again, if you already have that summer, forget about it. It doesn't matter, just focus on the future, right? Now, the best thing to do is you would get an internship at a top tier tech company, okay? Even if you don't want to work at like a Google, Microsoft, Facebook, you're like, nah, I want to do a startup. The best thing you can do for your tech career is get an internship at one of those places. Because once that's on your resume, everybody wants you, okay? Now, obviously, this is like best case scenario. Next case scenario is try to get an internship at some tech company, a local one, SaaS, working for the government, Infosys, right? That should be like your next tier. If you can't do that, then get an internship at a company doing something related to tech. And then a software development is better than IT, but IT is still something related to tech. So basically just like, essentially your goal is like, do the best you can, given what you have, to try to get as close as possible to a tech job, right? So these are like in order, like this is your ideal, but if you can't get this, then it's fine. Just like, if you can't get something, don't ever be like, damn, I suck. Just be like, well, I just didn't get that. Let's move on to like, what is the next thing? You know, how can I get closer every step of the way? The other thing you can do is, these are kind of like, I think around the same, you could do research. This is what I did. I failed my freshman summer. I did not get an internship at any tech company. My sophomore summer, I did not get an internship at any tech company. It was not until my junior summer, which is the last summer in a college career, that I did finally get an internship at a top tier tech company, AKA Google, okay? I applied to Google, Facebook, Meta, Uber, all these companies, the other internships. I did not get it because I was not good enough, but that's fine. I ended up finding this very last one, which is I did research with professors at my school, or just something, you know, like do something. My first research, I learned Python because the project was Python. It did not help me to do my interviews, but it helped me get better at programming. Okay. My second summer, I did research where I learned Java and R. Did not help me in my interviews at all, but it helped me get better at programming, okay? The last thing you can do is, if you can't find any of this, you can do a personal project. Like you should just work on something and put that on your resume. But I think this is actually very, very hard. I think this is actually harder than these, because once you get to this point, it's all on you. Like you need to have the like commitment, dedication, schedule to be like, nobody's telling me what to do. I'm gonna wake up every day and I'm gonna work on this thing and I'm gonna get XYZ done. Whatever the project is, as long as it's in tech, put it on GitHub. Now, the last thing, you should always apply to tech jobs, even if you're not ready, okay? You should never wait until you're ready, because failing is not a bad thing. You can apply next year. So if you're a freshman, if you know freshman, just be like, just apply. If you fail, you'll learn how the interview works. And then you failed and you'll apply sophomore year. If you fail again, you'll apply junior year. If you fail again, you'll go get a master's and you'll apply, you know, your senior year. If you fail again, you'll apply your first year of your master's, right? You just keep trying. But the thing I mentioned, fitting recruiting cycles, is because each company has different times in the year when they're trying to hire the most people. And a lot of times early on, like at the very top of the funnel, I personally think a lot of that is luck rather than skill. There are a lot of very skilled people that do not get interviews from the very top of the funnel that I know personally. Why? because there's so many people applying at the top of the funnel. So if all you're doing is like having your resume and submitting it to a job application, there are literally hundreds of thousands of people doing that for 2,000 positions in Google. So that top of the funnel, no matter how good you are, you might not get a call back because you just dropped. Like they just don't see it. The system doesn't pick it up. Okay. So I'm going to talk about that a little bit. It is always more important to apply than be ready. That's what I'll say, because you want to think my interview process, if I fail, was just a learning experience. Okay. So the application process itself, okay, step 0, the timelines. Again, I want to emphasize this. Know your timelines for your target companies. I actually don't know all the timelines for all the companies because I only ever focus on applying to the top tier ones and then research. Okay. But I do know that for all the FANG or Mang or whatever you want to call them, Uber, Airbnb, all the Silicon Valley companies, most of their hiring for full-time positions, fresh out of college, actually comes from their internship class. Okay. So it is very hard, even if you're really good, to never have interned at a top tech company and then get a job at full time. And I'm not telling you this to be like, don't apply. I'm just telling you this so that you know that when you get rejected, it's probably because you were not an intern the summer before, right? Not because you're bad. So just, again, this is more to keep in mind. Again, you should still apply. You should always apply because you might get it. But most of their full-time people are coming from their internship class. In fact, during COVID, when that started in 2020, Facebook hired no one except interns that were returning. They stopped their hiring for new grads. Okay. I think Google has done something similar. Okay. So almost always 80% of their full-time employees are coming from their intern class, or they're coming from companies that already had, like they already have experience working for like a year or two at another company. Okay. And they're joining as like their entry level, right? Now, most interns are hired in the fall for these companies, okay? For other companies, it changes. But for Google, Facebook, Airbnb, their hiring cycle starts. So for the next summer, it starts in July. And most of the time, they are filling up by the end of the summer, okay? Now, again, I am not telling you this to be like, oh, now it's February. Why should I even bother applying? You should still apply. But I'm just letting you know that even though the application is still open, most of the recruiters I've ever worked with, at this point, they're like, I hit my goals for the year. I got my bonus on the number of people I needed to get in. They're not as incentivized to get you in anymore because they like hit their goals. So they will hire you if you happen to be one of those really exceptional kids that is like, wow, this guy just crushed the interview so hard that we cannot afford to let him pass. But if you apply during the cycle, you don't have to be that kid. You just have to be good enough, and they'll be like, we need people, so let's get you in, okay? Even if you missed it to apply, it's more important to apply at the right time. All right, so that's step 0 is just knowing this. So again, this only applies to the top tier tech companies. I do know for like other tiers, this usually my understanding is this cycle shifts forward. So like if you're applying February, December, like a lot of companies for this summer are still hiring, but a lot of the top companies have already kind of 99% filled up their classes, right? So you still apply, but just keep that in mind. So you want to know, like if you're a sophomore, if you have any younger siblings, friends, or anybody you know, and they're freshmen, they want to, whatever, if they're sophomore in the fall next year, you got to tell them, hey, you should start applying in the fall, even if you feel like you're not ready, right? Now, the second step when you're applying is essentially, there's like 3 different ways that you get looked at, and they all look at different things, okay? So at least for the big tech companies, again, I am not speaking for smaller companies. They probably have a different process. You actually might be more familiar with those processes. And what I encourage you to do is to apply and fail, because then you'll learn about how those processes work. And you'll be like, I know what they're looking for. I know what they want, okay? But for the big tech companies, the first thing they do is they screen your resume. So if you just submit your resume at the application portal, it actually is going to get automatically screened by some machine learning algorithm that is going to try to pick you out. And more likely than not, no matter how good you are, they're not ever going to look at you. So if you get rejected automatically, that literally just says you rolled the dice and they didn't pick you. That's mostly what it says. Okay. So what you want to do the fastest possible way is just avoid the resume screen. Like either get referred because you know someone at the company that can take your resume and give it to a recruiter, or during a recruiting fair, like whatever, give your resume to the recruiter. You need to get a human to look at your resume. Okay. If you're just applying online for these big competitive companies, at least there's a huge automated system before. And honestly, I think it's mostly random. I mean, I'm sure they look at some stuff, but it's okay. Also, for that same reason, you should optimize your resume for the job because there is an automated system looking at it. So they're looking for like keywords in the job description to match what your resume says, right? So I would avoid only applying online, but again, it's always better to apply than not apply. But if you can try to like, if you want to apply to Meta, just be like, Luis, I want to apply to Meta. Here's my resume. And then at least I can get it to a recruiter and then they'll at least look at it and be like, okay, this student is not a good fit right now, so let's reject them. Or hey, let's give them a chance in the interviews. Okay. So you skip the whole first step. Now, step 2 is going to be the technical interviews. Now, for the top tier tech companies, how do you know you're ready for the technical interviews? One, you're doing all the homework and you're having a lot of fun. This class itself is very important to a lot of the top tier companies. Again, I only know about the top tier ones, okay? For tier 1 companies, what I would use as a system is if I go to LeetCode or HackerRank and I can do 90% of the easies and half of the mediums, you probably have a good chance of passing the technical interview, okay? You don't have to do all of them. You just have to be able to do some of them. Most of the top tier tech companies, they're going to be asking you questions that are like those questions you see there for the technical portion. Now, I have heard that from some non-top tier companies, they ask different questions. I am not aware of what those questions are. I don't know how that works. This is why you want to always apply, even if you're not ready, because then you'll learn, okay, they ask a lot about polymorphism and class inheritance, and they want me to know X, Y, Z, okay? So do your research in the companies to figure out what is it that they want from the interview. Because have you, yeah. Yeah. Yeah.
So it's just like a simulation, and most of the time it's not always coding, but it's how like you prioritize health, and that is actually for me that most difficult.
Yeah. Yeah. So again, I encourage you guys to do this, talk to each other, because you can try to figure out what do the interviews look like. In my school, our extracurricular clubs actually had interview packets that alum from the club would come back and be like, by the way, I interviewed at this company. This is sort of the stuff they asked. This is what was weird. This is what was different. And they would share all of that with the freshmen. So these are the sort of resources that I don't know if you guys have access to it, but you should have them, okay? Or try to make them like personally and share with the other students. You are not like, you might think you're competing with each other, but you're like, the applicant pool is so broad, it is not that common. Like you are not competing with each other. Like Google will be happy to hire every single one from NCAP that is able to pass their interviews. It's not a problem. They hire so many people, they'd be like, yes, we'll take everyone from NCAP if they pass our interviews. Who you're competing with is basically the rest of the United States and the rest of the world. All right. So amongst yourselves, you should help each other. There is no like, if he does poorly on my interview, I'm gonna get it. It just does not, like Google does not even look at that. Okay. So just said that's what Harvard figured out, I guess, because they just give us all the answers basically, right? And like give us all the preparation we need, right? Again, like I said, if you go with 90%, 50% of medium, also cast a wide net. And the reason I say this is because it's a probability game, okay? You maximize your probability, but at the end of the day, there is no, like, even if I took the interviews as an entry-level engineer, I cannot guarantee I would get all those job offers from all these companies. I'll probably get 80% of them, but I know for a fact 20% will maybe not even look at my resume or will like not, like I'll fail the interview for whatever reason, okay? So the difference is that once somebody gives you a job offer, everybody else wants to jump on the train because you have now been approved with their seal of like, this person did well in this one company. So now everybody else is like, well, if they did well there, even if they don't do so well in our interview, they must have seen something that we didn't see. So we want to hire them. Okay. So that's why you cast a wide net, because once you get your foot in the door, it gets a little bit easier. Also for other tier companies, like just talk to people from that company if you can, because I don't know how their interview works. Like Amazon, for example, I had no idea that's actually how they work. So I've never interviewed at Amazon, but now you know from him, this is what the interview looks like. This is what you need to prepare for. And again, you should try to share this with other students, and other students should try to share their experience with like, oh, when I applied to Uber, this is what it looks like. Because again, you are not competing with people in this room or even the people at NCAP. You're competing with like the rest of the world, right? Now for behavioral interviews, this is a little bit easier. Actually, some internships don't even have them, but mostly you talk about your projects, your summer experience. So again, if you have something that you've done your summer every time, then that's good. All right, so I know I spent a lot of time on this, but a lot of you have been asking questions about this. Does anybody have like, so this is my take on the process and why you should always apply and always fail. And every time you fail, you should tell your friends and you should say, I failed. And this is why I failed. And this is all the stuff I did wrong. This is the question they asked me. Okay. This is recorded. Okay. You're not supposed to share the questions they ask you officially. Okay. So don't do that. Okay. But do help each other out as much as you can. Okay. Cool. All right. So that's it. Any questions? Yeah. Did I do? Not really, but both of the research projects that I was doing were on GitHub. So they were available as a project on the website. I don't actually think anybody even them, to be honest with you. So this is why I think personal projects are kind of like, it's like, I think personal projects, if you do them, actually help you become a better software engineer, but they do not help you pass the interview or get past the interview screen too much. You need to have something, either an internship or a research or a project. You have to have one thing that is like, this person has been working, like they don't just laze around in the summer and like do nothing. They do something, and they're doing something related to tech, right? You need to have that, but that's more like a checkbox of like, oh, they have it, so it means they're interested, right? Yeah, and that is weird. That is the weird thing about the process is like, there are things you can do that will make you a better software engineer, like writing programs, building your projects, writing out libraries, but they are not the things that the interviews are sometimes asking for. So you do need to optimize essentially like step by step, like do something during the summer. That's your first step. Next step, optimize for the interviews for the jobs you want. So what are they asking for? What do they want? Let me figure that out. Then after that, you would be like, okay, now how do I become a better software engineer, right? And honestly, that applies to anything you want in life. It's not even just getting a job, but a lot of it is you need to figure out what do people want from you. And then you need to position yourself in a way that is, I am now giving you what you want from me. Okay. It's called being flexible, being resilient. There's like a lot of fancy words people use for that. It's called being open, being, open-minded, being resilient. Yeah, basically. Right. So like anytime somebody throws a challenge, instead of you being like, well, I don't have to do that, I suck. You say like, oh, okay, well, what do you want from me? Oh, you want me to learn electrical engineering? Okay, I can learn electrical engineering, and then I'll give it to you. And that's actually how you create like the most value in the world, is when you find out what people need and then you give it to them. Okay. Anyway, so we spent a lot of time there. So it means our lecture today is going to be cut a little bit short, but that's fine. We're just going to be covering hash sets. You guys don't even care about that anyway. And hopefully this was a little helpful. I can always give you more advice. I can expand this resume. We can try to look into more detail. But again, the TLDRs are never wait until you're ready. You should try to apply during the timelines. It's good to fail because you learn. And then please, please, please just help each other out as much as you can while still abiding by any NDAs that you sign. Okay, cool. Any questions? Awesome. All right, let's get started. So homework 4 is due on Wednesday. Again, most of the homeworks I try to give you, a lot of it, the exercises cover material that you're supposed to know because you're taking a computer science analysis of algorithms class. The questions labeled as interview practice are trying to get you to practice for your interviews. They are not sufficient. If all you're doing is just doing the homework, that is not enough for you to get better at your interviews. Okay, just FYI. No lecture on Monday, another announcement. So Monday we have a mental health day. There's not going to be lecture for this class. Okay. Yeah, happy Valentine's Day. Happy Singles Day if you're single. That is a widely celebrated holiday in other countries. But yeah, either Happy Valentine's or Happy Singles Day. Cool. I will be holding a Q&A with Meta folks at the freshman colloquium during that time. So that's part of the reason why I didn't do lecture on Monday. It is from 12 to 12:50. So it's at the same time that we have this lecture in McNair 213. So if you want to hop in and join, I'm sure nobody's going to complain if you happen to be there, but you don't have to. You are free from lecture on Monday. All right. Lecture 13, hashing hash sets and hash maps. So before we get started, let's skip that. We finished last time talking about red-black trees. Your first homework assignment, actually has a question on red-black trees, which is going to be fun. We were talking about why we needed these rules. And we basically said that the rules that we came up with for red-black trees make it so that the tree is pretty balanced. The black nodes are balanced by definition, if you guys remember that, because we said for every single node, the path from a black node to the root is going to have the same number of black nodes. So by definition, the black nodes are balanced, and the red nodes are spread out, so they don't mess things up too much. So the red nodes are the ones that are giving us the extra flexibility that make this easy. Okay. Now we can maintain this property using insert delete by using rotations, and this is called the red-black structure, and it's a proxy for balance. It's just a little bit weaker than perfect balance, but it's actually easier, much easier to maintain. So again, this is a general theme you will see in algorithms, right? For medians of medians, we were like, well, ideally we could get the median, but could we get something that's just not exactly the median, but close enough? And that actually helps you a lot. So for a lot of problems, you will sometimes run, this is more on the research side, but you will run into things where like, ideally I would want X. I want perfectly balanced trees, but can I give that up just a little bit? And then that solves your problem. Okay, so intuitively, if we build a red-black tree that's unbalanced, okay, yeah, I'll just skip this one because we have a lot of stuff to cover. But the intuition behind it is that one path can be at most twice as long as the other because of the rules that we have. So we have the rule where from here to here, there must be exactly the same number of nodes as from this path, same number of black nodes as from this path to this path, right? So that means the black nodes, if you ignore the red ones, this tree is perfectly balanced, okay? But we also have a rule that says that the child of a red node cannot be another red node, right? So at best, this is the worst possible tree, like path that we could have, where we insert a red node in between every black node, which intuitively says the tree can be at most twice as tall as a perfectly balanced tree, okay? Yeah, so the conjecture is that the tree is actually 2 times log n. So the height of a perfectly balanced tree is log n. And we're saying a red-black tree is not perfectly balanced, but based on our rules, it can be at most twice as tall as a perfectly balanced tree. I'm going to skip the proof, but you guys can maybe look at it. It's a proof by induction. It has a little bit of math, but I'm just going to skip it. You don't need to know it. I won't ask you on a midterm about this. Let me skip that. But TLDR, this is great because that means that search in a red-black tree is immediately big O of log n because the height is 2 log n. So in general, searching a tree, even a binary search tree, BST, takes O of height of the tree. In the worst case, your height can be n because you just have a really bad tree. Okay, but if you use a red-black tree, it will balance itself out as you insert and delete. So the running time for insert and delete depends primarily on how long it takes for you to search for the node, okay? So that running time is also big O of log n. The only thing we want to make sure is that when we insert a node and when we delete a node, how much work is it to maintain this red-black tree property, right? That's the only thing that's changing. So for search, it's obvious it's log n, because you don't do anything to the tree. For insert and delete, the only question is, can we maintain the red blackness of the tree? Can we keep it valid, right, while deleting and inserting nodes in a way that does not cost too much, right? That is very essentially constant time, or it could be log n as well. But anyway, so it turns out that you can do this. I'm not going to go into the details of it, but what we learned is that red-black trees always have a height of at most 2 times log of n plus 1, which means they're big O of log n. Okay. As with any binary search tree, all operations are big O of the height. Okay. So all operations of red-black trees are big O of log n. And conclusion, if we look at sorted arrays or linked lists, and we look at our 3 operations that we might be interested in, binary search trees make us all happy because they're all log n. Whereas for some of these, we were happy because this was log n, and we were really happy because this was constant. You know, inserting into a linked list is constant time, but we were very sad about these that were linear time. And again, for context, linear is kind of bad compared to log n because O of a million, linear time, is a million. If you have n equal to a million for log, that's 20. Okay. So it is much better. So now today we're actually going to talk about hashing. So this is another data structure, very, very common that you use in a lot of interview questions. It is the standard unordered map in C++. A red-black tree is used for the standard ordered map in C++. Okay. But that's in the back end. You don't ever implement. I've never implemented a red-black tree myself. It's actually very, very tricky. There's a lot of cases you have to handle. I will not ask you to do that, but it is nice to be aware that they exist. But today we're going to talk about hashing. Yeah, question or no? Okay, I thought I saw somebody raise their hand. Hashing, they're not hash browns. I'm not talking about hash browns. We are not talking about hashtags either. Okay, that's not what when I say hashing, that's not what I mean. We're also not talking about this, which is interesting. Who knows what this hashing is? Yeah. Okay, so we're not talking about that. In fact, what we're talking about is this. This is hashing. So as you can see, the English language is like very overloaded. It's like the same word for so many things. Yeah, it's like function overloading when you have the same function, but it can accept many different inputs. Anyway, we are going to be talking about hashing. I'll describe exactly what that is in a little bit. So hash tables are another data structure that allows for really fast insert, delete, and search. So the 3 operations that we usually care about data structures, inserting, deleting, and searching, they're very similar. They do this just like self-balancing trees. The difference is that we can actually get better performance in expectation. Okay, so the thing we're giving up is red-black trees give us guaranteed deterministic performance for every single insert. It can at most be log n. There is no case where it'll ever be slower than that, right? Now, for hash tables, they're actually really, really good in practice. But you can have a case where they're bad, okay? And then we're going to talk about these 2 things. Not that important to know. Honestly, I have never met somebody that has made their own hash function because they're so difficult to make, but we're going to talk about how you could make your own hash function if you were stupid enough to try that, or if you're doing research in that field. Okay, cool. So the goal is we insert delete keys, insert 5. We want to like just put it into a hash table somewhere in some data structure. We want to be able to delete 4 just by removing it. And we want to be able to search for 52 by looking for it here. Be like, here it is, right? That's the goal. We want a new data structure to do that. We talked about how self-balancing binary trees do all of these in log n. It's pretty sweet. Hash tables do all of this in constant time. Expected constant time. Okay, all of the operations are constant time. Insert, delete, search. This is why hash tables are very, very common way to improve your algorithms. Because a lot of times you want to insert, you want to search, you want to delete things. And if you're using this one, you're going to have a log n in your running time. Because every time you insert, it costs you log n. Every time you delete, it costs you log n. But if you just switch it for this data structure that has the same API, your running time is constant for the inserts. So now your algorithm is probably faster, right? Again, this is the reason we can do this. It's like, it's not for free, is that this is expected time, which means sometimes it can actually be linear when you insert delete, okay? And we'll talk about those. But in practice, they are often almost always constant time, especially if you have a very well-designed hash table, which C++ provides it for a standard unordered map. Python, dictionaries, every language already provides a very well designed hash table that you can use, except C. Except C. C does not have it. You would have to implement it yourself, as far as I know. Cool. But any other higher level language like Java has HashTip, HashMap, outer map, they're already implemented for you. You should just use those. You should not try to implement your own, because as we'll see in this lecture, implementing your own can actually be very difficult. So one way to get O of n time is, let's say that all of my keys are in the range 1 through 9. You guys actually have a data structure that can insert, delete, and search in constant time if I tell you that my keys are in a fixed set, in a fixed range. Any ideas? Yeah. Similar to, yeah, it is similar to the idea that we use for counting sort and radix sort. What is the data structure? What would it look like? Yeah, you basically make an array that are your buckets. So you can make an array of size 9 because you know at most, yeah, you can make an array. I guess this is 0 to 8 because you know that at most your biggest key is 9. And then you can say, well, when I insert 9, 6, 3, 5, I'll just put them into their bucket, right? In an array, you can just look up the index, just works, right? I delete, I'll just remove it from its bucket because I can immediately look where it is. And then when I search, I'll just try to search for it in its bucket, right? Okay, this is called direct addressing. This is not good. It seems, well, if you know your keys are limited, this is pretty good. Okay, so if ahead of time for some reason you know your keys are going to be a certain range, then this is actually a pretty fine solution, right? The problem is, yeah, so this should look familiar. This is similar to what we used in counting sort. The problem is what happens when I have a lot of possible keys, right? Now, if I know my keys go up to 1 trillion or 1 billion, whatever that number is, I need to make an array that is that big, which is going to take gigabytes and gigabytes of memory. So it's like, it's not that good in that case, right? And the problem with hashing is that normally the set of possible keys that can go into your hash table is essentially ginormous. It's huge. It's like a lot of them are possible. Okay. So solution, again, similar to radix sort, you might think of this solution and be like, well, I can actually put the buckets based on a single digit. So that limits my hash table to be from 1 to 9, right? And then my key for every value is just going to be its digit. So if I have these, I can insert 2 into the 1 bucket, 21 into the 1 bucket, 345 into the 5 bucket. So I'm basically hashing them by the last digit, right? So again, these are like examples where, like, if I asked you a question, like, you guys have you know everything already to kind of think of something like this, okay? So this is what it would look like. And now I search for 21. So if I'm saying, like, where's 21? Then I look at the first digit, that takes me to this bucket. And then I immediately see, like, oh, 21 is here. So I'm done. It is there. Okay. What's the problem with this approach? Yeah, right there. Exactly. That's exactly the problem with this approach. So the problem is, say I give you this sequence of numbers. So 22 goes here, 352, they all go into the same bucket, and they're not ordered in any way. They're ordered in the way they were given to my data structure, right? So now when I'm looking for 2, or like for 22 or whatever, I can find 22 really quickly because it'll be the first one in the bucket. But if I'm looking for 2, then I have to iterate over the all of the elements. So it'll be O of n, right? But that was a hash table. That is essentially what a hash table is. It is exactly what we did. It has buckets where it puts stuff into, and for every value, it has a way to take that value and create a key for it. And the way we did it in that example is we said, well, just look at the last digit. That is your key. All right. So every hash table, that is actually what a hash table is. So you guys created a hash table. The problem with your hash table is that your key function is terrible. Okay. The way you take the value and make a key out of it is bad. So it's not a very good one. You can be more clever, and it will result in fast insert, delete, and search, all like in expectation. Like no matter what order I give you of insert, delete, because there's some randomness, it'll be very fast. So yeah. It's another possible hash function. Yes, to be like, instead of taking the first digit, you could say, well, I take my key and I just count how many digits it has, right? And that tells me which bucket it goes into. I wouldn't say it's better. I would actually say it's about the same. So what we will see, or I don't know, you should convince yourself that any deterministic hash function, so any hash function that given an input does the exact same thing, like gives you the exact same key, is bad. Because again, what we're trying to do is you're trying to prevent somebody from being able to give me certain inputs. So in your case, if you're saying my hash function is count the number of digits, then I will just give you inserts that are all 3 digits long, and then they all go into the same bucket. And then you're like, well, maybe I can do like the second digit, and I'll be, well, I'll just give you numbers where the second digit is the same, right? And intuitively, we won't prove it or anything, but intuitively, you should see why, if there's any function that is not random, that does not use randomness, if it's like fixed, then I can come up with a sequence of inputs that will mess up your function. Okay. So the problem is that our universe, we're going to call it U, we're going to say it's of size M. Okay. This is our universe is like all the possible keys. All the possible values I want to hash, right? And generally, it is really, really big. Okay. But the thing we know is that usually when we hash elements, we're going to hash n of them. And n is actually pretty small compared to m. Okay. That is the assumption that hash tables are going to make, which is almost always true if you think about it, because even if you're hashing 1,000,000 strings or 1 billion, that is a very small fraction of all the possible strings that could exist of a certain length, right? So the other problem is we don't know which ones are going to show up. Again, if you know in advance which keys you're going to see, then you can actually just make an array with like have those exact keys. There's an easier way to solve it. So the problems we're having is that the universe is really big. We know we're going to see only a small subset of all the possible ones, but we don't know which subset it's going to be, right? So here's an example. If U is the set of strings of at most 280 ASCII characters, so this would be like unique IDs, let's say, there are 128 to the 280 of them, which is a ginormous number, like just huge. More than the number of atoms in the universe multiplied by 3 million times or something. So it's just too big, okay? That is all the possible strings. However, the only ones I would care about are the hashtags that are used in Twitter. So again, there are a lot of hashtags used in Twitter. There's probably millions, maybe even billions of them. But compared to this number, this is really small. Okay. Cool. So what we use is we use a hash function, which essentially is what you guys came up with the count and sort, and what Isaiah mentioned with like, let me count the number of digits. It is a hash function that is going to take one of my elements from my universe, and it's going to map it to some bucket, to some number, 1 to n. That's all hash functions do. They take some value and then they give you a number out of it. Okay. For this lecture, yeah, let's not worry about this. But what we did say is that one example, the least significant digit of x, that is a valid hash function. It is a bad hash function, but it is a hash function. Okay. Now hash tables, I'm going to skip this slide. Yeah, so some of this should be reviewed, but basically like if you get multiple elements in a bucket, you can have like a linked list. So that's one way to do it. Another way to do it is you can use something called open addressing, where like instead of being like, oh, there's something already here, what you do is when you insert the 43, you'll just put it like in the next open bucket. So you'll do something like this. So there's like different techniques to deal with like collisions. That's all these slides we're covering. but we're gonna skip them. It's not that important. Again, you're never gonna implement your own hash table unless you're working in C or something that doesn't already have them. But it is important to know that their running time is constant, expected, insert, delete, all of it, okay? Cool. So again, so ideally what we want from a hash table is we want this. When we insert keys into it, we want them to be pretty evenly distributed amongst our table, because that's good for us. This is really bad for us. If all the inserts go to the same bucket, that's where our running time gets bad for search and delete, right? Woo! We also don't want there to be too many buckets, because then the hash table takes a lot of space, right? So we could make a hash table that's the size of the universe, and then just say every element in my universe, right? You just map to you're like number 1, and then the next one is number 2, and that's your bucket. But then your hash table is like you're storing the entire universe, so you know, not good, right? Pretty spread out. This means that search, insert, and delete will be fast. Okay. So this is our goal. So as we've discussed for hash tables, the thing that matters is the hash function. So our goal for the hash function is we want a hash function that no matter what n elements a bad guy chooses, so no matter the sequence of elements they give you, the buckets are going to be pretty balanced. So they're never going to end up in the same bucket, no matter the sequence. And if we had this hash function, we would actually have our hash table with constant insert, delete, and search. Does that make sense to everyone? Right. So now our goal is like we wanted to design this data structure that had constant delete and search. We tried it a few times, and then we came up with examples where it didn't work very well. And we said, well, actually, what really matters is how good is our hash function, right? So now we're like, forget about the tables. Let's focus on the hash functions, right? And you will see that it's like a very common thing you do in computer science is like, once you figure out you really need to solve a smaller problem, you're like, forget about everything else. Let me solve this smaller one, right? Question, can you come up with such a function? What do you guys think? I'll tell you no. The answer is no. The answer is no, you cannot. Unless you've seen it before, the answer is no. And if you can, I guess if you had like a really good math background, maybe you could if you tried really hard, but you can't. And first of all, the thing that I mentioned before is that it's impossible for any deterministic hash function. Does anybody have questions about that? So if I have a hash function that is deterministic, there's no randomness. It is impossible for this to be a good hash function. Why? Yeah, Lester. Yeah. Yeah. Why? Because if it's deterministic, what a bad guy can do, is this a good diagram? Okay, I'll just have it completely. What a bad guy can do is he can just try a bunch of elements in our deterministic. So deterministic means that if I give you the same value, you're going to give me the same key every single time, right? Every single time. So a bad guy can just take our function and be like, well, let me try you in like a bunch of values. And your hash function is pretty good. So let's say it like it spreads them out across the buckets. But eventually your bad guy is going to find 2 values that go to the same bucket, right? It's just like by definition, your bucket is too small. So let's say your buckets are like there's n of them. Your bad guy just tries it on 2 n values. And now every bucket will have, in the best case, it'll have 2 things in it, right? So what the bad guy says is, well, let me pick one of these buckets, ignore all the other values I tried. I will ask you to insert only these 2 elements that I know go to the same bucket. So now he's like only inserting 2 things into your table, but in order to find them, they go to the same bucket. So it's linear in the number of inserts. Okay. So, yeah, I don't know. Does that sort of make sense to folks a little bit? Right. So if it's deterministic, he can just try a bunch of them until he finds a bunch of them that go to the same bucket. And then he can say, okay, forget all the other ones I gave you. Right. Yeah. So what that would do is like what we're trying to avoid is we're trying to avoid in a worst case scenario where I give you 5 elements. And then in order to search for one of those elements, it takes you 5 steps. We're trying to avoid that. So what he would do is he would say, here's a million elements. And then maybe searching for one of them takes 5 steps, which is actually good, right? You actually want that. But then he'll say like, oh, okay, forget all the other elements that didn't go to the same bucket. I'll just give you these 5 now. So now your data structure only has the 5 that went to the same bucket. And then when you search for one, it'll take 5 steps in the worst case, right? So now he's, yeah. Yeah, so the hash tables you will ever use that have already solved this problem are O of 1. So in your practice, when you look and you see unordered map, you should be, this is going to be O of 1 for insert, delete, everything. But what we're doing here is we're trying to think of like, what if we wanted to design our own hash table? And basically, if the hash table used a deterministic function, it's actually impossible to get O of 1. Right? Because actually what matters for the hash tables is not, I guess it's not correct to say like hash tables are O of 1. What matters is like hash tables with specific hash functions are O of 1. If you have a bad hash function, your hash table is going to be bad. Okay, cool. The solution is you actually introduce a little bit of randomness. So we're not going to cover all of this, but let's see, what is the important stuff here? Random hash function. Yeah, we are not going to get to finish this today. Well, let's just keep going and maybe we'll continue on Tuesday. Maybe I'll just skip it completely because it's important for you to know for the class. But honestly, I have never met somebody that has ever designed their own hash table because it's hard. So you just use the ones that already exist. But the solution is randomness. So the game you pick, it's again, the game we're thinking about is that somebody is choosing the n elements from your big universe, and they're going to give them to you in any sequence. So he's going to say like, insert these elements, right? And what you want is your algorithm is going to have a random hash function. So you're going to roll some dice to pick a hash function. That's one way to think about it being random. And then you're going to use that random hash function to hash your elements. Okay, so in this case, the reason this helps is because we are not considering the case where the adversary can control our randomness. Okay, so he cannot control what we roll in the dice. So that's why it's like, if we have a random hash function, then he cannot predict where the elements are going to hash to. So he can never create an example that is too bad as long as our hash function is good, right? So I guess what we'll do is here's an example of a uniformly random hash function, which means the hash of the first element in my universe is going to be some random number between 1 and n. Okay, so this is actually a really good hash function. It is completely uniformly random, right? Now, the problem with this hash function is that whatever. Nope. Nope, let's skip that. Okay. That's a lot of stuff. I want to skip a lot of this stuff, but because we're at 12:50, so I don't want to keep you guys too much longer. Okay, we will end it here, which is, this is a really good hash function, actually. The rest, so we'll start on Tuesday, on Wednesday, next Wednesday, because there's no lecture on Monday. We're going to cover why this is a good hash function, but intuitively, this is a good hash function because it's defined such that every value gets mapped to a uniformly random number. Okay, now this hash function is actually very bad hash function because like it's good in the sense that it gives us expected of 1 time. But it is bad in the sense that to define this function, you need a lot of space because every number is uniformly random. So like, you need to like save it somewhere, and you need to have an answer for every possible element in your universe, which means the definition of your hash function is going to be bigger than your hash table. So you're like, what's the point? It defeats the point. But it is a good hash function that we can use to analyze. So essentially what we're going to do on Tuesday is we're going to start with this like ideal hash function, which is like, if it was uniformly random, it would be great. And then what we're going to do is we're going to say, well, if it's uniformly random, we get all the properties we want. What if it was a little bit less random? Could we get all the properties we want and not have to store every single value of the function, right? Cool. All right, so that's it for Friday. I guess that's expected that we didn't finish because I did spend a lot of time. We actually only had like 10 more slides, 15 more slides. I did spend a lot of time talking about applying to jobs. Is that something you want me to do more of, or? Oh, okay. Okay, if you guys have questions about jobs, like shoot me an email. I will try to prepare a lecture where we talk more about that. It is also important for you guys to learn some of this stuff, but not important in the like, it's gonna get me a job and like make me make more money. It's more important in the like, it helps exercise your way of thinking, and like, it's a little bit more abstract, right? But yeah. All right, everyone on Zoom, thanks for joining. I'll see you guys. Class is over, and enjoy your Monday lecture off. I will be in the freshman colloquiums, so if you want to come, if you miss my voice, then you can come hear me there. Yeah, that's up.
So, competencies were something.